So I want to talk about ELF files. I don't use any ELF files. First of all, when it just-in-time compiles, why don't you stop and think about just-in-time, how you would do it? Okay, so we have a symbol table. If we have a global variable in the symbol table, or we have okay, so how would you so now we have two symbols, a global variable and a function. So ask yourself, first of all, you need to know what a symbol table is. I use a hash table. Do you know what a hash table is? No, you probably don't, because they keep it secret. A hash table is an array. Let's say, well, it's an array of hash pointers. And a hash pointer is, I'm not explaining this well. It's an array of linked lists. Okay. Now, let's say you have 26 linked lists for the letters of the alphabet, A to Z. So if you had an array, let's say U0 pointer, array, hash, array 26. Now the problem, now let's say you had commands or you had symbols, and you said, okay, well, if it starts with M, we're going to put it in, what's M's number? I don't know, 20 or something, not 20, 17, I don't know what it is. Anyway, M, if you have I, you put it in the I array. We have, if you had 26 letters, okay? What happens if you have two of them that start with I? Well, what you do is you have your first one, and then it points to the second one, a linked list. Second one that starts with I. Okay, so a hash table, we're just using the letter of the alphabet. What I use is the letter of the alphabet shifted over to for each new letter. So, and I use a big array. So if I say hash, I have a, let's go to the kernel. So I have a hash function, hash string. You give it a pointer to a string, and it adds what? It shifts and then adds. Shifts and adds. It loads all the bytes, shifts and adds. So you end up with a number. Okay, so let's get back to making a just-in-time compiler. So let's say you want to, I'm going to turn on my just-in-time compiler. I'm going to call my function. Now, what did we have to do in order to make this work? Well, we had to parse it, and we started with a token. We have a token there, and then we have a semicolon. Anyway, so we looked in the symbol table, and in the symbol table we found this number. Okay, that's the code address for that function. If we unassemble at that number, it's a push call, and this is the string. Remember what this does. It does what? So actually, I'm looking at the wrong thing. I'm looking at unassemble. That's the unassemble. This is my function. Push, call, pop, return. Okay, So we want to make a call to this address. So the way that so we have to make an array with an E83B000000C3. How did we come up with that number 3B? Well, it's a relative offset. So that means we say 0x that minus the current address, the address of the code, comma 0x, but we have to add 4 or 5, uh-oh, pop quiz. Okay, so the answer is 3B. You add the address after the instruction. So we need an offset of 3B. So this is just calling some code that's very close to the my function code. The allocator slices off a little bit, and it just sliced off a little bit for that. And then we need a C3. So now that you know, so a just-in-time compiler looks in the symbol table and makes an offset. This is not that hard, folks. It's easy doing a just-in-time compiler. It's a lot easier than making an ELF file, for heaven's sakes. So I made a mini compiler just to show how it's done. This is only a couple hundred lines. And what this does, 1 plus 2 plus 3 times 4 plus 5. Okay, so this does a stack machine. So if you come over here, it pushes 1, pushes 3, pops 2 and adds. So it adds 2 and 3, then it pushes 5, pushes 4, then it pops 2 and multiplies, so 5 and 4 is 20. Then it pushes, then it adds 21, and then 5, and then it gets 26. Okay, so this code right here, this is the machine code. We don't do an interpreter. We do a true compiler makes machine code. If you look right here, this is the machine code. So each operation either pops 2 and does an operation and then pushes. So we start with a lex, which is what converts it to tokens. So the lex just makes it a little easier. If it's an operator, it returns the operator. If it's an integer, it converts to decimal a bunch of digits to get a number. If it's a label, like a symbol table label, then it returns a string. Then to do the operations, we have to either handle the operator or delay the operator based on the precedence. So and we have to handle parentheses. And so this little bit of code, it's on my distribution. Now I'm special because my page tables are all identity mapped and they're read, write, execute. So I can just actually I have to put it in the code heap. I have to allocate it from the code heap. That's this thing right here. FS is the current task. So I ask for 512 bytes from the code heap. That means it's going to be within 2 gig, the bottom 2 gig. And then when I'm done, I do a call to the code that I compiled. Okay, so just-in-time compiling is really easy. Now, to make ahead of time, all I do is I collect together exported symbols. As a matter of fact, I have I used to distribute this, but I took it off. I don't want my users making binaries. I want them to use just-in-time. Okay? I don't want my users making binaries. So there's no reason for you to make a binary. You only need 2 binaries. So I have a function called binrep. I'm going to go to the you do not need to make binaries. So if I say doc max, that makes the keyboard, that makes the command line infinite number of lines for the command line. Then we say this is a code. I used to distribute this, but I don't distribute it anymore because you do not need to make binaries. So this is a report on the kernel. So the kernel has its own symbol table. It's a list of imports and exports. First of all, my kernel can be loaded at any address, and each of these offsets has to be patched. So with the you have to add the base address of the module. So if you load the kernel in a new place, you have to patch all these little bits of code. So my binary files are big, but that doesn't matter. They're position independent and they get patched. So the kernel patches itself before it starts running, or when at the first part of when it runs. I have export symbols, which is in my binary starts with the raw binary code, and then it has a symbol table at the end, and they're with the patch table, and these are export symbols, and so these are all placed into the symbol table for the binary. And believe it or not, my kernel has some imports that start out unresolved. They're not resolved until you load the compiler module. Then these imports get resolved. So if you want to see where I do my binary, when the kernel starts up, when it's starting up and it's in real mode, it switches to 32-bit mode, and then it starts patching. It goes through that list of absolute addresses, and it loads the offset, adds a module base, and stores it. So you can't run any C code until you patch it, because the compiler, or any absolute addresses, you can't use any absolute addresses until you patch it. Okay, then it jumps down to C code. I said that wrong. Okay, so the compiler, mostly you should be making just-in-time, and there's no mystery about just-in-time. When you're making ahead of time a binary module, it's just a flat binary. It puts the code right next to, it puts the code in order as it compiles, and it makes a patch table with these imports and exports. And then when you load, it patches those absolute addresses and fills in the table. Then when it starts compiling, it compiles the header, and this associates this binds the function to the offset in the symbol table. So it looks for dir file name in the symbol table that got loaded already. So so first in the startup, it patches the absolute addresses. Then it goes and adds all those symbols for export symbols into the Atom symbol table. And then if we do a who, you'll notice there's a, oh, I delete it. That's what I do. So over here, if you see an export symbol, that's one of the originals. I think I overwrite the old export. I'm a little bit confused. So these start as export symbols, and then when you bind, there's a new symbol. Is that clear? Did I say that right? Let's see where. Print. Let's look for print. Okay, so it's a function. Okay, so it's not showing the export symbol. It started with an export symbol, and then it added a function header to bind, So now there's a map file. Okay, let's go to the kernel. When you make a binary, there is no make utility. This is laughably funny. All it is a bunch of includes for code. So it includes, and the raw binary is made in this exact order, and it makes a map file. The map file has, you can't see it, but there's a the line numbers for the line numbers are stored in this map file. It's called a it's similar to how an image is stored, a binary image. Where is it? I'm a little bit confused. This is a link. There should be binary images. Control FBI equals. Okay. These that have the binary image. Anyway, I just used the same file format. So during boot in your accounts directory, if you use the standard, then it loads map file load kernel, map file load compiler. So we have source debugging available. So if I say unassemble print, that has source line numbers stored. So that's from the map file. So there's only two binary files that ever need to be created: kernel and compiler. You never need to make a binary. They're flat binary. You can make one if you want. You can play with it. You use the compile command, and then you use. Let's make a binary just to show you. Okay, so to make a binary, I wonder if this is going to work. Okay. Extern u0 print colon, or let's do put char to be safe. I think we say import. We say I might crash this. Let's I'm gonna lie and okay. No, I'm not. I60. Okay. Then let's do put chars. What? Okay. So we're going to try and make this into a binary. Okay, put chars, import. So we say compile test.cpp.z. Expecting type. Oh, it doesn't even know the type. Those have to be defined. You have to include the headers. We're not going to do that. We're going to say internal type. Internal. Okay. Now we say compile. Okay, so we compiled it. So now we have a binary that's 4E long. Now if we say load test.bin.c. That did not work. Okay, I don't know what happened. Don't mess with it. Oh, okay. We'll. Now I guess I have to figure this out. Well, that's not fun. I'm at a loss. Because if we say put chars test, that works. Okay. about let's look at the binary. So I go to archive, binrep, load. Where is it? Load, or include. Now we go and binrep. Let's go home. Binrep test.bin. Okay, so it imports put chars. It has a main at 0. Is this put chars U16? I wonder if I took out support. I don't think so. I'll try that again. Oh, okay. No, that's not good. I could unnecessary. Oh well. Anyway, you don't need to mess with binaries. Okay, fine. I'll look at star B equals file read test bin.c dump B. Okay. So there's a header which is 16 bytes. Then there's the what. The main. If we do a binrep. Binrep. Okay, dump. Okay, so there's a main at offset 0. So if we unassemble function, unassemble starting at B plus, there's a header 16. I think that's the problem. No, the header is 1E. 1E off of the current location. Plus 2. 1E plus 2 is 20. Okay, so it's moving. That looks peculiar. It's waiting to get patched with the put chars. Oh, that's the characters I did. Wat, then it's pushing, then it's calling put chars. It wants to get patched. So the put chars is at offset C. So 20C, 2. So here's a 1020 C is right about here. So that's correct. Let's see if I did load correctly. Maybe there's a file name flags. Okay, I think. Okay, I give up.